and I will start sharing my screen. Okay. All right. Okay, I guess we're all set. So from now on, the lecture is recorded. Every 5 minutes or so, I will go and check the Zoom link to see if new people are trying to join, and I will admit them. So welcome everybody to ENGR 371. As I just said, I really hope that we can continue this course in lecture, because this is a difficult course, and I think it really helps if we can, do the lectures in class. So this is the syllabus. The syllabus is also available. Let me see if I can move my window. Yeah, there you go. So the syllabus is also available on the web. I really encourage you to read the syllabus line by line, because there are many important information in the syllabus. So the midterm exam is on Wednesday, February 23. It's scheduled to be in class. Of course, assuming that we return to in-class lectures. So make sure you mark your calendars for midterm, and it will be from chapters 2 and 3. There are 2 grading schemes. Scheme 1, so let me see if I can use the pen. Yeah, I can. So in scheme 1, the midterm is worth 20%, and in scheme B, the midterm is worth 0%. Instead, all of its weight is on the final exam. And you will have to do a project for this course. Again, for now, we have assumed that the course will return to in-person lectures. There is a POD. POD stands for Programmer on Duty. So it's basically a TA who will help you with your project. You will have to do projects in groups of 4. If you do not form a group, the TA will randomly assign you to a group. See, and the groups cannot change, and you have to write a proposal for your project before you start doing the project. So let me see if I mentioned the deadline for that. Yeah, so the deadline for this to form your groups is sometime at the end of January. I thought I had mentioned it here, but it's in the syllabus. So you have to form your groups by a certain date towards the end of January. So there are tutorials this week. For the first week, there are no tutorials. So the tutorials start from week 2. So the TAs will solve sample questions during tutorials. And another important thing that will happen during tutorial is that there will be 4 quizzes that are held during the tutorial, and only the best 3 out of these 4 quizzes will count towards your final grade. So if you get sick and miss one of the quizzes, or if you miss a quiz for any other reason, you will not lose any points. So that was all the logistics that I wanted to cover. I guess now it's a good time to admit the people who okay, there you go. So let me admit everybody who joined during the lecture. So I see somebody raised hand. I will unmute you, and then you can ask the question. So yeah, you can go ahead.
Morning, Professor. I just had a question regarding the quizzes. Are we going to know in advance when the quizzes will be, or will they be given randomly throughout the semester?
Yeah, so yeah, good question. So make sure you do read the syllabus. The exact time of the 4 quizzes are written in the syllabus. So no, they are not randomly. They are basically, the dates are known. And I will let you know during the lecture that remind you that next week there's a quiz. Make sure you attend the quiz.
Okay, perfect. And are the projects going to be done during tutorial time, or is it on our own time?
No, so the
because
project
you said the TA is going to help us.
Yeah, so the project will be done at your time, during your own time, and you will start basically data collection and all of that after the midterm. Before the midterm, you don't really do much. All you do before midterm is form your groups and decide what project you want to work on. So I will also post like a handout for the project on Moodle.
Okay, perfect. Thank you so much, Professor.
Yeah, sure. All right. So so at this point, I will basically, if anybody joins now, there's a high chance that I may not be able to see you. So it's already almost 15 minutes past. Okay. So let me start. Okay. Oops. All right. So we will start with chapter 2, which first in chapter 2, we talk about counting techniques, and then we will talk about how to calculate probabilities. So first, we introduce the concept of sample space. The set of all possible outcomes of a random experiment is called the sample space, and we denote it as S. And S is discrete if it consists of a finite set of countable outcomes, and is continuous if it basically contains an interval of real numbers. For example, if we are looking at, go back. So for example, if the experiment is flipping a coin, then the sample space is discrete because the outcomes are heads or tails, right? Or if we are rolling a die, the outcome is, the sample space is discrete, is numbers from 1 to 6. But if the random experiment, for example, is the length of some device that's being produced, for example, the length of this pen, or the length of somebody that we select randomly, like the height of somebody that we select randomly in class, that is a continuous random variable because the length is can be any number. Or for example, if our experiment is how long it takes until the next customer enters Tim Hortons, then that time is also a continuous random variable. So consider this experiment where we select a camera and record the recycle time of the flash. And suppose that it's known that all recycle times are between 1.5 and 5 seconds. Then S is between 1 and 5 and 5 seconds. And sorry, X, which is the time that it takes to recharge, is between 1 and 5 seconds. So let's assume that in this experiment, we are not really interested in the exact time that it takes to recharge the camera. For example, we are only interested in classifying the recharge as low, medium, or high, right? For example, we want to send them for further processing if the recharge time is high. So in this case, for the same experiment, then the recycle time would be a discrete random variable because we only have 3 outcomes. Or let's say we want to see whether a camera's flash recharge time conforms to the time specifications. In that case, our sample space again is discrete, is yes or no. So in another experiment, assume that we are looking at the messages which arrive either on time or late. And let's say that in total, we have 3 messages that are being sent, right? So in this case, our sample space is the following. either all three of them are on time, or the first two are on time and the last one is late, and so forth, right? So basically what I have done here is that I have written the sample space as a set, right? Another way we can do that is by writing the sample space as in a tree. So here is the basically root, and we say that message one, we decide for the message one at the root node. So we say message one can be on time or late. And if the message one is on time, then message two again can be on time or late, right? And again, if message two is also on time, then message three can be again on time or late, right? So this basically, this path of the tree, O denotes to this basically member of this set, right? And I really encourage you to start getting comfortable with these tree diagrams, because these are very powerful ways to analyze, problems, even very, very complex problems that are, harder than the scope of this course. So these are very powerful tools that you can use to visualize, your problem. And again, for your midterm and final exams, again, some problems that are, hard to visualize with this technique, you can really see what's going on. So let me try to. There are a few more people who have joined late. Let me try to admit them. So since this is the first lecture, I will allow people who joined late to basically be connected, but it's very distracting for me, because I see like a pop-up over there and I have to stop sharing and then continue sharing again. So starting from the next class, if you are more than 5 minutes late, I will not be able to let you in, because it's not fair to the students who started on time. Okay. And as I said, I really hope that this is very temporary and we return to, why does it do this? We return to in-class lectures. Okay. All right. So an event is a certain subset of the sample space, right? So for example, for the case of previous example, right? So we wrote that this is the entire sample space, and assume that we call the event, we define event E as all of the outcomes where all of the messages are on time. So in this case, event E only has one member, which is OOO, right? So I defined E as a set where all of the messages arrive on time. So events are sets. Because of that, we can define union for these events, right? So union means that either outcomes in event one happen or the outcomes in event two happen, right? So, and here or is a mathematical or, right? It means that like either one of them is fine, right? So if both of them are happen, that's also fine, right? So that's the difference between mathematical or and like the or that we may use in English. And we denote union with this symbol, union. We define also intersection. That means that both the events should happen, and the keyword here is and we denote that with this symbol. And we also have complement. So complement is basically means that all the outcomes that are not in a certain event, right? And they are denoted as E prime, right? So here we have the prime. Okay. So suppose that the recycle time of two cameras are recorded, and consider only whether the cameras conform to the manufacturing standards or not, right? So we have two cameras, and the cameras either conform or they do not conform, right? So the sample space is going to be yes, yes, both of them conform, yes, no. First one conforms, the second one doesn't. No, why? The first one doesn't, the second one does, and no, neither conforms, right? And now I denote event 1 as the event that at least one of the cameras conform, right? So this then event 1 is going to be YY, both of them conform, YN or NY, right? And suppose that I define event 2 as the event that no camera conforms, right? Then E2 is going to be NN. So now suppose that I define event 3 as an event that at least one camera does not conform, right? So that means that YN, NY, and NN, right? So because in this set, at least one of them doesn't conform. And we want to calculate the union of E1 and E3. So to calculate the union, I have to write down all of the members of the set. And remember, in a set, no member can be repeated twice, right? So then the union is going to be, so first I'm going to write the members of E1 because the union contains all of them. So YY, YN, and NY, right? And then I'm going to add members of event 3 that are not already here. So YN is already here, NY is already here, NN is not here, so I'm going to add that, right? And when we look at this, in fact, the union is going to be the same set as the sample space, right? So because all of the outcomes of the sample space are here. Intersection means the events that are in both of them. So I'm going to start with YY. So is YY in E1? Yes. Is it also in E3? No, it's not. So YY is not going to be written here. Now I'm going to move to YN. YN is here. YN is also here. So I'm going to write YN. And then NY is here. NY is also here. So I'm going to write NY as well, right? And then finally, E1 prime, all the events that are not in E1, and that's going to be NN. It only has one member. So the answers are also here. So now an example for a continuous sample space. So here event 1 is if X is between 10 and 12, and event 2 is with basically the outcome of X being between 11 and 15, right? So one way that makes these problems much easier again is to draw the interval, right? So we are going to do that. The entire interval is from 10 to 15. So from 10 to 15, right? And then I'm going to write E1 with the purple color. So E1 is from 10 to 12. So from 10, and if it does include a number, I'm going to denote it with a full circle. So that is 10, and then 10 to 12 is going to be around here. So this is 12. And then event 2 is between 11 and 15. So I'm going to write event 2 with the green color. So event 2 is going to be from 11. So this is 11 to 15. Right. So this is event 2, and this is event 1. Right. So now the union is going to be quite easy to compute based on these graphs. It's going to be anything between 10 and 15. 15 is not included because this is an empty circle. The intersection is going to be this part, right, between 11 and 12, and the complement of E1. Here the question, so whenever you want to calculate the complement, you have to see what is the sample space, right? So the question says the sample space are all positive numbers. So anything is not in E1, so that's going to be all numbers between 0 and 10. So I'm going to draw E1 prime here. We haven't used, so let's use yellow. So 0, 10, and then 12. So event 1 prime is going to be between 0 to 10. P1 prime, or so I'm looking here at event 1, this was full, so for prime this will be empty, and then for 12 this is empty, so the circle here is going to be full, right? So this goes all the way to infinity. So event 1 prime, or complement of event 1, is going to be the union of these two intervals. Okay, so Venn diagrams help you calculate intersections and unions, basically operations on sets much more easily than doing it in your head. So usually we write sample space. We denote the sample space as a big rectangle, and all of the events are inside them. So here we have two events, A and B. So the union is going to be basically all parts of A and B. The intersection is going to be the areas that they share. And then we can do more complex operations. For example, here we are doing A union B. So everything in A and B, which is going to be this part. And then intersection of that with C. So we are going to look at what part of this basically area intersects with C, and that's going to be this part only, right? So this is the final answer, right? Or we can, for example, do A intersection C and then complements. So what we do is we always do step by step. First we say, okay, what is A intersection C? That's going to be this area, and complement means anything outside of that area. So basically our answer is going to be all of this area. So we define two events as mutually exclusive if they share no common outcome, right? So here we can see two events A and B that they share no common outcome, right? So here we have A and B, and as we can see, there's nothing common between them, right? And symbolically, we show A intersection B is equal to an empty set. So again, as we see, A and B share nothing in common. So let's look at some examples of mutually exclusive events. For example, we are rolling a die. I call event 1 as the number 1 comes up, and I basically denote event 2 as number 2 basically comes up, right? So here in this case, event 1 is number 1, right? And event 2 is number 2, right? So these two sets are, event 1 and event 2 are mutually exclusive because we can't get 1 and 2 at the same time, right? Or let's say a driver arrives at an intersection, and the event of turning, whether the driver turns left, let's call that event 1, and driver turns right, we call that event 2. These two events are mutually exclusive. Now, an example of two events that are not mutually exclusive. So we define event 1 as, for example, turning right at that intersection, and event 2 as scratching your head, when you're at the intersection. So these two events are not mutually exclusive because somebody, can scratch her head and turn left at the same time or right at the same time. Right. So another example. So let's say we have a deck of cards. We defined event A as getting an ace. We are basically looking at the card randomly, right? So we define ace, like the event ace as getting an ace, and we define event K as getting a king, right? So these two events are mutually exclusive because a card cannot be ace and king simultaneously, right? But let's say in another experiment, in this case, we define event A as picking a card that is hard, and event B as picking a card. So this is our event A, and we define event B as getting a card that's a king, right? In this case, these two events are not mutually exclusive because we might pick the king of hearts, right? So they do have an intersection. So I think you guys are already familiar with De Morgan laws. So we will go through them quickly. So complement of intersection. So complement of union. So A union B complement is going to be A prime intersection B prime. And also the complement of intersection is going to be, the events are going to be complemented, and then intersection is going to be converted into a union, right? And finally, complement of complement is the original set. So if we apply complement twice, we arrive back at the original set. So, so far, what we talked about, I think most of you guys were familiar with, and it's quite possible that you have started phasing out, which is okay, because we haven't really covered, difficult topics so far. But I really encourage you to pay attention from now on, because this is the part that the course gets interesting and also very confusing, right? So make sure that you pay close attention from this point. So we now start talking about counting techniques, right? So there are 3 techniques that we use for counting. The first one is multiplication. The second one is permutation, and the third one is combination, right? So it's very, very important that you learn which technique you should use for a particular problem. Okay, so I see there are a few more people who joined later. Let me okay, so for the students who joined the lecture late, I mentioned it before, I will mention it again. It is not easy for me to do that, because I'm using my iPad to write here. And because of that, my laptop is, basically the keyboard is disabled. And that means that admitting people who arrive late is a bit difficult, because I have to disconnect and then use my laptop to admit people and then connect back. So because it's distracting, I will not do that in the next lecture. So make sure that you do not arrive more than 5 minutes late. So I will start the lecture, and at 10:20, whoever arrives late, I will let them in. And after 10:20, I will not let anybody in, because it's distracting to me and also to everybody else who is in class. Okay. All right. So the first one, which may sound easy, but in my opinion is the most important one, because if you master the first one, you can derive the other ones based on the first technique, is the multiplication rule. So let's say that I want to do an operation that consists of k steps, and there are n1 ways to complete step 1, and n2 ways to complete step 2, and basically ... and nk ways to complete step k, right? Then the total number of ways that's possible to perform this task is n1 times n2 times ... times nk, right? So what's important here to remember is that to basically to complete this task, we must do all of these k steps, right? So our task consists of completing all of these k steps, right? So we have to do all of them, and in the other words, there's an and between. So let's look at an example. Assume that you are designing a website, and we can choose to use among 4 colors. So basically the color for our text. So we have to choose the color. We have to choose the font, which font we are using. And also we have to choose where to place an image, right? So we have 3 places for the image, right? So this basically task consists of 3 steps. And we want to see how many designs are possible. So the answer, since we have to do all of them, we have to choose a color and we have to choose a font and we have to pick a place. Then the answer is 4 times 3 times 3, which is 36 ways to complete this task, right? So like another example, let's say you want to design a watch, right? And you have, 3 choices for the color of the band, right? Of the watch band, and you have, let's say 5 types of bands. And also the watches come in 2 different sizes, the actual watch face. So two options of the actual watch size, right? So since we have to pick a color for the band and we have to choose a type of band and we have to choose the size of the watch, the answer, how many watches are there available? The answer is going to be 3 times 5 times 2, which is 30, right? So there are 30 options available here, right? So the next counting technique is permutation, and it basically finds the number of ordered sequences of elements of a set, right? So for example, let's say that my set consists of 3 characters, A, B, and C. Then there are 6 permutations, right? And it's always good to basically see what those 6 permutations are. So first I have ABC, then I have ACB, BAC, BCA, CAB, and CBA, right? So how did I calculate this, right? How did I say there are 6 permutations, right? The answer to this question, the equation for number of permutations is n factorial, right? So here I had, my set had 3 members. So the answer is going to be 3 factorial, which is 6. Why? Because 3 factorial is equal to 3 times 2 times 1, right? So whenever you want to count the number of permutations, ordered permutations, then you have to use the factorial equation. By the way, all of these equations are provided in a crib sheet that I will post on Moodle. The crib sheet will also be provided during the midterm and final exams. So that means that you don't really need to memorize any equation, but you do need to know which equation to use, after reading the question. So for example, after reading this question, how many ordered sets are there with basically these characters, A, B, and C? You have to remember that you have to use the permutation rule, which is the factorial, right? So it's important to know why this equation is correct, right? Why n factorial, right? And the reason for that is the following. So I have a set that has n members, and I want to write, basically, I want to write how many permutations are there, how many ordered permutations, right? So I have, let's say, object 1, object 2, all the way to object n, right? Yeah, perhaps it's better to not write it as generic as this. Let's write it in a different way. So let me do something. Okay. Oh. Okay. So let's try to basically solve a bit like another example. So here, assume that I have a set that consists of these numbers, 1, 2, 3, 4, right? And I want to see how many 4-digit numbers I can create with these 4 numbers, 1, 2, and 4, right? For example, one possible outcome is 1, 2, 3, 4, right? 1,234. So this is acceptable. But for example, this is not acceptable. 1, 1, 2, 3. This is not acceptable because I don't have 2 ones, right? I only have 1, 1, right? So to find that out, so now we know that the equation for that is n factorial. So the answer of how many 4 digits numbers I can create with these 4 numbers is going to be 4 factorial, right? But I think that's not important. What is more important is to know how to attack this type of problems, right? So we say that, okay, I'm interested in 4-digit numbers, right? So I have 4 places to fill up, right? The most significant digit, and then the digit after that, and so forth, right? I have to fill up these 4 digits. How many options do I have for the first location? So for the first location, I can place 1, 2, 3, or 4. So I have 4 locations here, right? And to create a 4-digit number, I have to fill up the first digit and the second digit. So I have to also count how many ways I can do this one. So for this one, I only have 3 options because I have already used one of the digits in the first location, right? So one of the digits has been used here. Now I'm left with only 3 digits. So this guy here has 3 options. And then similarly, this guy here has only 2 options because two basically numbers have already been used here and here. So I have 2 options here. And finally here, I only have 1 options because 3 numbers have already been used here. So there's only one letter left here. So here I have 1 option left. And since I have to basically to create a 4-digit number, I have to fill up the first location and the second location and the third location and the fourth location. So since there's and basically is synonymous with multiplication. So I have to multiply this, right? And what is this? This is 4 factorial, right? So you saw that I used the multiplication rule to basically prove this equation, right? So that's why I said the first rule is the most important rule in my opinion, because you can solve any problem, no matter how difficult, just using the multiplication rule. Okay. So the next problem is I want to count. Basically, I want to perform a subset permutation, right? So I have a sequence of n items, and I want to create. I have n items, and I want to create a sequence of r items out of that, right? So let's look at an example to see how we can attack this problem. So we want to see how many 3-letter words we can make with characters from A to Z. And no repetition is allowed, right? So AAB, for example, is not acceptable, right? So let's try to solve this question again using the multiplication rule, right? So I will say that, okay, I have to basically create 3-letter words. So that means that I have to fill up location 1, location 2, and location 3, right? So, and I have a total of 26 characters, right? From A to Z. Yeah, my memory is a bit, I think there's 26 characters, right? This is funny. Yeah. Yeah, so if you see like one difficulty of teaching online, if we were in class, I could quickly confirm with you, right? So yeah, I have a total of 26, basically 26 characters to choose from A to Z. So that means that for the first, to fill up the first location, I have 26 options, right? And since I have used one of them in the first location, for the next one, I only have 25 locations, right? And to fill up the third one, since I've used 2 of them before, I have 24 options, right? So this is the final answer, 26 times 25 times 24, right? So the equation that we are going to give for this is going to be, so I'm going to write this as the following. This is going to be 26 times 25 times ... times 1 divided by 23 times 22 times dot 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 times 1, right? So the reason for that is that these two are equal because 23 and so forth will be canceled out, right? So this basically, this equality is correct. And now what is this? This is equal to 26 factorial divided by 23 factorial, right? So this is the equation actually for subset permutation, right? So we finished this question. So this part is not really needed. You know, this could be written as the final answer because I can punch this into my calculator, right, and see the final answer. Now, let's say if it's possible to solve the exact same question using a different approach, right? So in blue, I try to solve it using another approach. So basically, what I'm going to say is that, okay, I'm going to look at the characters, right? So I'm going to say, okay, I have character A, I have character B, all the way, I have character Z, right? And basically, I'm going to solve this for characters, right? So I'm going to say, okay, character A has, how many options does character A have, right? So character A can either be in the first location, or it can be in the second location, or it can be in the third location. And there is a fourth option. Character A may not be used at all, right? So perhaps what I can do is I can like draw like an auxiliary location here. Oops, sorry, I wanted to try with different color. So not used, right? So I can say that A can be assigned to here, first place, second place, third place, or basically I don't have to use A, right? So I can place it into like not used bin, right? So the difference between the last one is that last one is bigger. I can place many, you know, characters here, but these three, I can only place one character here, right? So A has 4 options. So I will say, okay, A has 4 options. Let me see how many options I have for B. So when I look at B, again, B can be in any one of these, right? But the problem here is that here I can't really write how many options I have for B because I don't know whether A was already used here, 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 or it was here. If A was here, like in the last location, then B has 4 options again, because again, B can be here, 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 or here, right? But if A was already used, you know, in one of these locations that actually matter, then B only has 3 options, right? So we see that this solution already breaks up because I can't really continue. Like for B, I don't really know how many options I have, right? And the problem even gets worse for C, because for C, I either have 4 options or 3 options or 2 options, right? So basically, this approach does fail, right? I can't really approach it from the perspective of the characters, right? So in real problems that you solve in real world and also in this course, you have to learn to approach the problem from different angles, right? And if one of them doesn't work, you have to, you have to be able to change your approach, right? To solve it using an approach that does work. Okay. So basically, the solution that we did here in this part, we have an equation for this, right? Oh, because this is the last slide. Okay. All right. So let me